This paper explores whether foundation models, which are excellent at tasks like predicting the next word in a sentence, actually develop a deep understanding of the world. We'll discuss a new technique for testing this. The key question is whether these models are just skilled mimics, or if they have learned the fundamental rules that govern the data they see, much like the leap from Kepler's observations to Newton's laws of physics. Here we see a clear example of the problem. A powerful transformer model was trained to predict how planets move. It got very good at predicting the trajectories. But when researchers tested if it understood the why, the actual forces of gravity, it failed spectacularly. The model essentially invented its own, incorrect laws of physics. This highlights the core issue. A model can seem smart by making good predictions, but it might not have learned the real-world rules at all. To address this, the paper proposes a testing procedure called an inductive bias probe. Think of it as a scientific experiment on the AI model. We feed the model small, specially created datasets that follow a known set of rules, like a simplified version of physics. Then, we check if the model's learned behavior from this new data matches the rules it was supposed to learn. This helps us see if the model's internal logic aligns with the real world's logic. The probe uses two key measurements. The first, called RIB, checks if the model respects states. This means that if two different situations are fundamentally the same according to the rules, the model should treat them the same. The second, DIB, checks if the model can distinguish between different states. If two situations are truly different, the model should recognize that. A good model needs to score well on both metrics to prove it understands the rules. Let's return to the orbital mechanics experiment. A transformer model was trained extensively on data from thousands of simulated solar systems. It got incredibly good at predicting where planets would be. But the inductive bias probe revealed its understanding was shallow. It hadn't learned Newton's laws. When pushed to generalize, it invented different, nonsensical physical laws for different situations, showing it hadn't formed a coherent, universal model of physics. This isn't just about physics. The researchers tested models on other rule-based systems, like a simple movement game and the board game Othello. The results were similar. Even when the models learned to play by the rules perfectly, the probe showed they hadn't learned the fundamental state of the game, like the position of all the pieces on the board. Instead, they seemed to take shortcuts, learning just enough to predict the next legal move, not the entire game state. In summary, this research reveals a critical gap in our foundation models. While they are powerful predictors, they often don't build a deep, genuine understanding of the rules governing their data. They tend to learn clever shortcuts and heuristics that work for specific tasks, but fail to generalize. The inductive bias probe gives us a way to measure this gap. The ultimate goal is to figure out how to build models that don't just predict, but truly understand. Sources: